Okay, so we are here to celebrate the 50th anniversary of the large-scale structure of space-time, the first and greatest of the monographs on global structure in general relativity. Emanuele has cautioned me to be brief in these introductory remarks so that we actually have time for the speakers to give their talks. Our first speaker is George Ellis. George got his PhD back in 1964, working with Dennis Sciama at Cambridge. He is now a professor emeritus at University of Cape Town. He is a fellow of the Royal Society. He has been awarded the Templeton Prize, as well as the Prix Georges Lemaitre and the Order of the Star of South Africa. And in addition to all those other honors, he is also a past president of the GRG Society, having served from 89 to 92. He's, perhaps best known as one of the authors of this book that we're celebrating, but I want to mention that he also has a very long and distinguished research program in physical cosmology, which is basically an effort to keep the cosmologists honest. And as part of that, he's come up with a beautiful set of gauge invariant cosmological perturbation variables, which all cosmologists should use, even though most of them don't. As a byproduct of some of this cosmology stuff, I want to mention that he's also come up with a wonderful set of scale invariant variables that are good for describing space-time singularities. Okay, so I could say a lot more, but in the interest of brevity, let me turn it over to George, who can start his talk.
Okay, well, thank you very much for the honor of this meeting. It's very much appreciated. So I'm going to share a screen, a set of notes, and here we go. And so what now this, yeah. So this was a result of my collaboration with Stephen Hawking, and it was, we were encouraged by Dennis Sciama, our research supervisor, and it was built strongly on the work of Roger Penrose, but it builds on the work. Sorry?
Please remember to mute yourselves when you come into the Zoom room, or we're going to have these problems. Thank you. Go ahead, George. I'm sorry.
Yeah, okay. It builds on the work of a successive generation of pioneers in geometry and physics. And the book presents as an integrated whole a global understanding of space-time structure as it was at that time. And the underlying issue is the tension between geometrical and analytic approaches to studying properties of space-time. And this book strongly takes a geometric approach and is still cited by many today. Now, what I want to do is I'm going to talk about from the physics and then the geometry, and I want to talk about what I think is three different groups of people who are important in the physics, the people on whom this is all built. And of course, the first group laid the foundations, and of course, the most important was Albert Einstein with the whole idea of general relativity, the principal equivalence, the field equations, and all of that. So he, of course, laid the foundations for everything else that all of us are doing. Then Carl Schwarzschild, the first exact solution, Willem de Sitter, Arthur Eddington, Alexander Friedman, Georges Lemaitre, H.P. Robertson, A.C.G. Walker, Richard Tolman, and Hermann Weyl. This is what I would regard as the first group of people who set up the field equations and then started finding out the solutions to them, many of which are still important today. De Sitter space is important, and so on. Friedman and then Lemaitre discovered the idea of the expanding universe. And of course, Einstein's biggest error was denying both of them. When both of them showed their work to Einstein, he denied that this made physical sense. And then Robertson and Walker put it together. Tolman wrote some very interesting stuff, and Hermann Weyl played a very interesting role. Now, the key points here is the idea of tensor equations in general coordinates was set up and used by all of them. The summation convention made a great deal of difference and specific important solutions. Now, the second group of people who I would like to mention were the people who developed on those foundations. And J.L. Singh was very important, and he particularly developed the geodesic deviation equation, which was in Singh and Schilt in 1949. Kurt Gödel played this very remarkable role when he was at the Institute of Advanced Studies, and he used to talk with Einstein about this, and he produced the first rotating solution, as far as I know, exact rotating solution, and he introduced this whole stuff about causality in GR because the Gödel solution has closed time-like lines, and this set in motion the whole study of causal structures. There was Ray Chowdhury, quite remarkable. Out of nowhere, Ray Chowdhury developed his basic gravitational equation, which plays a key role in cosmology. And basically, he came out of left field. And I still have no idea, maybe someone can enlighten us about how he came to be thinking about this and developed this. Engelbert Schucking was a very interesting person playing a role behind all of this, and he was very, very well read. He gave a lot of advice to many people. Indeed, he gave advice to Roger Penrose, and he wrote very little, but his work was really significant. George Ellis was, to me, one of my heroes. He developed in detail the 1+3 covariant methods for looking at relativistic fluids. His paper on that is, to my mind, one of the most beautiful in general relativity. And he was with the Hamburg group, which include Ray Sachs. And then they interacted with Felix Pirani, who played a really key role by emphasizing the physical significance of the Weil tensor. Manfred Trumper was part of the Hamburg group and developed the full Bianchi identities. And behind all of this, also an interesting thing was Erwin Schrödinger, who played, he developed a very nice discussion of the global structure of the De Sitter universe. And he also had a very interesting book called Space-Time Structure. Now, the key points in the second lot of here, as opposed to the first lot, was the importance of tensor symmetries, the idea of skew symmetric, symmetric parts, trace-free parts, and so on. And this hadn't been appreciated before. And this was related to group representations and also the permutation tensor identities, which enable you to develop a lot of the identities which people use. This all led to the importance of the Weil tensor as well as the Ricci tensor. Until this time, this was all based on the Ricci tensor alone. Now the Weil tensor came into its own, and the full Bianchi identities as integrability conditions on the field equations. And these could be written in a 1+3 covariant form, which Manfred Trumper developed. Now, the third group started looking at the global methods, and Finkelstein was one of the people who looked at this. Eddington and Finkelstein, their Eddington-Finkelstein coordinates were the first go at the Schwarzschild singularity. Martin Kruskel played a very important role with his maximal extension of the Schwarzschild solution. And Wolfgang Rindler had a beautiful paper on horizons, which is still one of the best papers on horizons to get into the subject of horizons in generic nature of horizons in both cosmology and black holes. The key person, of course, who blew the whole subject open with Roger Penrose diagrams, the global methods, his enormously important paper in 1965, inequalities rather than equalities, energy conditions, closed trapped surfaces and light cone geometry. Roger was the enormous pioneer. And then Stephen developed and extended the work of Roger Penrose by taking what Roger had done for black holes and applying it towards the idea of cosmology. Other people who took part in this, and I may miss out some, but these are the ones who come to mind, was Brandon Carter, who did very important work on maximal extensions or all sorts of solutions and the killing tensors. Charles Misner did good work on the geometry of caustics, which Roger had also written about. Werner Israel came up with the first, again, out of the blue, the first black hole uniqueness theorem, a quite remarkable theorem. Bob Garoche was in London working with Roger on global properties and Yvonne Choquet-Bluha on the global existence theorem. So this was the second look. And the key ideas that I want to mention here is the idea of a coordinate atlas covering a manifold. And the idea of an atlas was central to all of this. And then domains of dimensions, Cauchy surfaces, and the relation to geodesic equation existence. So this was the third group where global methods were brought in and related to stuff such as the existence of geodesics and domains of dependence. Now, on the mathematics side, the pioneers who enabled all of this, even before Einstein, Gauss, Carl Friedrich Gauss, and then Bernhard Riemann, the central figure in all of this, Riemann's spaces, but he was developing on ideas from Gauss and his very celebrated paper on this. Ricci, Gregorio Ricci, Elwin Christoffel symbols, and Tullio Levi-Civita. These were the people who were the pioneers on the mathematics side, with Riemann playing the absolutely central role, but responding to Gauss, and then developed by these people who developed a lot of what we've been talking about, covariant equations and so on. The developers were people like Eisenhardt. The books that I read, Eisenhardt's book on Riemannian geometry, which was a very badly written book, but nevertheless, it was a book that's available. And then J.A. Schouten, his book on Ricci calculus, which was a brilliant book, and talked about, in particular, about generalized basis, general coordinates. Now, and then the coordinate-free methods, a book that I learned a lot about this from was Sigurd Helveson, a book called Differential Geometry in Symmetric Spaces, a very great book, and a book by P.M. Cohn called Lie Groups. And these introduced me to the coordinate-free methods, which I then introduced to the Cambridge group. Now, the Hawking and Penrose theorems were summarized. They both wrote Adams Prize essays, but the Adams Prize essays were not formally published. I and Stephen decided to develop this book, giving a systematic basis for understanding the global methods, because there were these theorems, there were these papers. Penrose and Hawking had done a slew of theorems, but in order to understand them, you had to get into a lot of background stuff. So we just signed a contract with CUP in 1987. We started writing in earnest in 1970 and completed in 1973. Now, remember, this was the days before LaTeX, and so you had to type the stuff, you had to write in the equations by hand because you didn't have LaTeX, and that meant that you sent the stuff off to the press, they sent you the proofs, and you had to check the proofs line by line with your draft manuscript, mark in the corrections, send them back, and then they would send back a second round, and then eventually you would reach a steady state when the new set of errors introduced by the process is the same as the number you corrected. Incidentally, the diagrams of the book, which played an important role, were done by a draftsman in the geography department on the basis of my instructions, and we should have mentioned him in our introductions to the book. I regret that we didn't, but the diagrams played an important part in the book. Now, what was not included in the book? We didn't deal with gravitational radiation, which Einstein had introduced way, way back, but it hadn't yet become an important topic. We didn't deal with alternative theories of gravity experimental tests. We didn't deal with structure formation, and of course not with inflationary cosmology, which hadn't yet started. We didn't deal with black hole thermodynamics and Hawking radiation, and we didn't deal with quantum gravity. Now, it's important to mention that, of course, this was not the only influential book on general relativity. Stephen Weinsberg's book preceded us. Misner, Thorne, and Wheeler, which you have celebrated, was the same year. Our year was the same year. Radu and Verno, 1992. Bob Watt, 2010. And many others that I couldn't, but these are just the one which particularly come to mind. Now, what I want to emphasize is the underlying tension, is the tension between geometrical and analytic approaches. And Weinberg's book is a book which doesn't like to talk about geometry. He likes to talk about analytic method. And because of the way he approaches it, you can't even ask the kind of global questions that are related to domains of dependence. Penrose is, of course, essentially geometric, but backed up by analytic estimates and calculations. And we followed that approach. It's a very geometrical book, but which is why it's got so many pictures, but it is backed up by analytic calculations. In the end, the analytic methods failed to give the answer to the question about initial singularities, and the geometric topological methods won as regards the singularity theorems. And I speak with feeling about this. I spent a lot of time trying to, as other people did, like Larry Shepley, trying to develop, use Bianchi models as an example, and trying to find if the Bianchi models could be used to develop, prove or disprove the singularity theorems. The Ray-Chowdhury equation couldn't, because if you had rotation, the Ray-Chowdhury equation said maybe you had a singularity, maybe not. If you had acceleration, it said maybe, maybe not. And the geometric and topological methods won. Now, the final thing about this, the major question in the book, is there a singular start to the universe, is unanswered today, because we no longer believe in the strong energy condition. And the reason we don't believe in the strong energy condition anymore is a widespread belief in inflation universe models, where the strong energy condition is violated by effective scalar fields. So we have a good reason to believe in the very early universe. At the time when we want to use the singularity theorems, the energy condition doesn't hold. And so that is kind of a rather strange thing. But of course, we did say in the book that we understood that in the end, supposing that you believe the singularity theorems, what they indicated was not actually a space-time singularity, but that you needed to turn to a quantum gravity theory. And various people who are with us are experts in quantum gravity theories, and they have still not quite solved the issue. And finally, this book is, interestingly, still referred to by many each year, as you can see from Google Scholar. It is still read by a lot of people, even as we speak today. So that is what I wanted to introduce about the book and the way that it works. And by the way, I'm very happy to see a whole number of friends here who I haven't seen for a very long time, quite a few of them.
Okay, great. Thanks very much for that talk. Emanuele, do we want to take some questions now, or do we want to have the next talk and hold questions till the end?
Maybe we could have a few right now before Abhay starts, if Abhay is okay with it. Just a couple.
Yes, certainly fine.
Okay, so who would like to ask something?
I have a question for George. Hi, George.
Hi.
Where the large in the title is coming from?
Where does the large come? Well, the small scale structure is quantum gravity, and so the large scale structure is where you need local methods. And so the whole point about it is it wasn't just a textbook on using tensor calculus to study space-time. It was about the global stuff, which is domains of dependence, where geodesics could get to, where they couldn't get to, and all of that kind of thing. Are there Cauchy surfaces? These are the kind of questions. Those are all questions to do with the large-scale structure of the universe.
This is large as opposed to quantum, I guess, right? Okay, thanks, George.
Okay, so we have a question from Yunji Ma. Go ahead and unmute yourself and ask your question.
Hello, yes, Professor George Ellis. Yes, I'm Inje Ma from Stellenbosch University of South Africa. So I just, I see you said by the time you did not include gravitational radiation and inflation cosmology and so on. And there are so many, interesting developments after, several years after maybe 1980s. So you and Stephen Hawking didn't think to update your book by including more recent development?
No, that's a very good question. We were asked at one point to update it, and we didn't for two reasons. One is we were both looking really at quite different questions. Now, it would have been a very large work, but it got more and more difficult working with Stephen as he was having more and more difficulty talking. I was in a different continent than he was. And so we were asked about updating it. And basically, it was just became impractical. And in any case, there were other books which came in which did deal with this. For instance, I think Bob Walt's book did a lot of the stuff which we might have done if we had done extra work. But to deal with something like gravitational radiation, you can do it in a very cursory fashion. To do it in an adequate fashion is a very substantial job.
Thank you.
Okay, so I think we have a question from Satya also. So why don't you go ahead and unmute yourself?
Mine was very, very similar, David. So let me keep it very brief. Thank you very much, George, for this wonderful historical review. If you were to give up on strong energy condition, is there anything else from the point of view of cosmology that you would still impose, or do you think the question really remains open and we need more observational data? On the contrary, the fact that we don't need, we can't impose strong energy condition, is that saying something about cosmological observations? Some hints about problem cosmology?
Well, firstly, we did have a brief mention of the fact in the book. We mentioned very briefly that a scalar field could violate the energy conditions. And we said something like it would happen on such a small scale, it wouldn't be important. That is because we hadn't foreseen the idea of inflation. There's a huge difference between the strong energy condition and the weak energy condition. Now, the strong energy condition is rho plus 3p greater than naught, and that can be violated. The weak energy condition is rho plus p, and that should not be violated by any serious physical theory. That's for very many reasons. And I'm emphasizing this, and this is something that David and I feel is quite strongly about. If you violate the weak energy conditions, several things happen. The inertial mass density is negative. So you push the thing that way and it rushes off that way, which means everything is incredibly unstable. If it expands, the density goes up, not down. So this is completely wrong. And I believe if you take George Ellis's beautiful article about relativistic hydrodynamics, you will find that the second law of thermodynamics is violated if you take the relativistic version. So it is absolutely wrong. It should be an absolute no-no to violate the second, the rho plus p. Greater than now, you will find the two things, that some investigations of dark energy do violate this. And I think this is very, very unacceptable. It also, some of the stuff going on about traversable wormholes and all of that kind of stuff also violated. And I think that this is a definite reason for saying all of that stuff is wrong, because violating the weak energy conditions completely different from violating the strong energy conditions. I think this is a very important issue.
Thank you very much. Wonderful.
Yeah, so actually, let me sort of abuse my my power as chair to sort of follow up on Satya's question. So first of all, I agree with you completely about the strong energy condition and the weak energy condition. But as you know, Robertson-Walker has trapped surfaces, and so one can apply the Penrose singularity theorem using only the weak energy condition or even the null energy condition. So why isn't that enough for saying that cosmologies have singularities?
Well, with Roy Martins and some others, I pointed out that once you've got the strong energy condition violated, you can have cosmological models where there is no singularity. And of course, if you look at the initial paper by Robertson, who classified all of the models, he had non-singular models. They did a bounce. And you can get a bounce if you violate the strong energy condition and you have K is +1. And this is also something one must emphasize. Models with K is +1 have completely different behavior than models with K is -1 or K is 0. And there is an alleged theorem which says that you have to have singularities in inflationary universes. And that theorem is a theorem which I do not believe, because it is a theorem in which the result is built into the conditions. And I could explain that in detail, but perhaps this is not the place to do that.
Okay, great. Thanks very much. All right, so let's go ahead and move on to the next talk. So let me give. So our next talk is by Abhay Ashtekar, and again, I've been admonished by Emanuele to be brief. So there's a whole bunch of stuff that I could say that I won't. So Abhay got his PhD in 1978. At the University of Chicago, working with Bob Garrosh. He's currently Professor Emeritus at Penn State. He's been awarded the APS Einstein Prize. He's been elected a member of the U.S. National Academy of Sciences. And in addition, he is also a past president of the GRG Society, serving from 2007 through 2010. He's most known as the father of loop quantum gravity, having come up with the Ashtekar variables and applying them in an ambitious and long-standing research program to quantize gravity. But I want to mention that even before that, he had done some groundbreaking work on coming up with a comprehensive formalism for asymptotically flat spacetimes. And even, while spearheading this entire program of loop quantum gravity, he's also found time to have a research program on local horizons and on the properties of gravitational radiation that have been very useful as well. On a more personal note, I want to mention that for those of us who followed Abhay as University of Chicago relativity graduate students, that Abhay, together with Gary Horowitz, were sort of held up to us as the unattainable ideal. In other words, this is who you should strive to emulate, even though we know for sure that you're going to fall far short. Okay, so with that, I want to turn everything over to Abhay to give his talk.
Okay, can you hear me?
Yes.
Thank you, David, for this introduction, last part of which I don't believe, but it doesn't matter. David also mentioned that I got my PhD in 78. I just wanted to say that is correct, because that's when I got my diploma, but actually I finished my work in 74 and went on to the postdoc with Roger Penrose at that time. This is relevant because, in fact, the monograph that we are celebrating right now really came out, therefore, in the last year of my graduate school. And so it really made a deep impression on me and also all other people of my generation. And in fact, it really, in many ways, shaped the way that we think about general relativity, not only my generation, but the subsequent generations. Now, we are actually celebrating the 50th anniversary of the publication of this Hawking-Ellis monograph. But I would like to begin by going back even further to 100 years ago, when the same press, Cambridge University Press, published this monograph by Eddington, The Mathematical Theory of Relativity. And in fact, even Einstein himself said that this was the finest presentation of the subject in any language at the time it appeared. Now I'm going back to this monograph in part because it will really help us understand the impact of the Hawking-Ellis monograph, because we can see the developments in our field during the 5 decades between Eddington's monograph and that of Hawking-Ellis, and then the subsequent 5 decades since the publication of Hawking-Ellis itself. So, as I said, that sorry, on the slide, as I said, the Cambridge University Press published this, perhaps the first detailed and authoritative monograph on general relativity written by Eddington. It was written only 8 years after Einstein's discovery of the theory and 4 years after the solar eclipse expedition, which was also led by Eddington himself, and which provided the first empirical proof for general theory for general relativity, and really served to catapult it as a revolution. What you see here is one of the first editions, a vintage edition, and you'll find in the internet it is for sale for several $100s. So in case you want to buy it, you can still get it. So the monograph is a comprehensive treatment of general relativity on 3 fronts. Eddington systematically introduces the tools of tensor calculus, explains the then known physical consequences of the theory, and with really admirable clarity, and discusses in detail the conceptual underpinning of general relativity. And these 3 things actually intermingle very seamlessly in the monograph. So it's a marvelous book for the time when it was written. Eddington stresses that investigation of the external world in physics is a quest for structure rather than substance. And as we'll see later, in a real sense, the same theme is repeated in Hawking and Ellis. The main application of general relativity discussed in the monograph is what is widely known, what was then widely known in cosmology. Let me just try to see if I can get rid of something in my screen because I cannot. Good. The main application of general relativity discussed in the monograph is what was then widely known in cosmology. But there is also an in-depth and excellent discussion of linearized gravitational waves and the 2 polarizations of these gravitational waves. Now, I think there is a lot of popular account which says that Eddington really didn't believe in gravitational waves because he thought they were traveling at the speed of light. And that is incorrect. The monograph actually really clearly states that the physical modes travel with the speed of light. And when he talks about traveling with the speed of thought, he's talking about gauge modes because their velocity depends on the speed of on the choice of gauge. The monograph does have some important limitations, but it remained a leading source for general relativity for well over 3 decades. And then the renaissance of general relativity came up, and that made it obsolete. Now, I would like to spend just a little time to say a couple of words about Renaissance, because this word is used in very different senses in very different senses. In the history and philosophy of science circles, there has been a great deal of, and occasionally rather heated discussion of the meaning of renaissance of general relativity and paradigm shift and the conditions that caused it. This is, for example, really discussed in some great detail in the volume edited by Bloom, Lally, and Wren, called Renaissance of General Relativity in Context. And there are 2 sets of reasons are given in these books by historians of science as to what led to this renaissance. And the first is called Sugar Daddy, and that means that there was an increase in funding for science in the post-Sputnik era. And the second is called Sleeping Beauty, that general relativity was awakened because of the serendipitous astrophysical and cosmological discoveries. I'm referring to slightly something else, and really is because I'm really talking about the brand new conceptual and mathematical tools introduced in the 60s and 70s that led to physically important insights, enabling explorations of unseen phenomena. And the point is that these developments were simulated, the one that I'm talking about, conceptual and mathematical ones, they were really stimulated by the boost that the field received from astrophysical and cosmological observations, but caused a conceptual shift in our collective thinking in their own right. For example, singularity theorems that established the inevitability of the initial singularity within classical general relativity provided a precise formulation of what black hole is. This is another example of this conceptual shift, which we did not have before, and then led to black hole uniqueness theorem and gave us coordinate invariant description of gravitational waves in full nonlinear general relativity. In turn, the conceptual shift in cosmology led people to move away from the steady state paradigm and seek detailed observations and signatures of the phenomena in the early universe. So really, although it is conceptual and mathematical tools, they really did have direct impact on how we formulate physical questions and what we look for and what the observers then were led to discover, were motivated to discover. So here are two examples that I have given, which really are records of this paradigm shift that I just mentioned. The first is a description from the internet of the proceedings of the 1967 Battelle rencontre, which are edited by John Wheeler and Cecil David, and that was held in Seattle. Here are some key phrases that you see. You see Cauchy horizon, you see geometrical dynamics, you see the hypersurfaces, globally hyperbolic equations, you see Lie groups, you see manifolds, null geodesics, superspace, the topology, space-time and spinor structures, vector bundles, and so on. And these ideas prominently featured in the lectures by David, Garrosh, Misner, and Penrose during this 1967 Battelle rencontre. And the second example is the book by Roger Penrose, in which he collected the rich set of novel techniques that he had developed and used in his research in the 1960s. It provided a brand new syntax to explore the global issues in general relativity, especially in presence of strong gravity. This paradigm shift was occurring as Stephen Hawking and George Ellis were busy writing their monograph to introduce the paradigm shift to younger generation of researchers in a comprehensive fashion. And this new syntax actually really came from the mixture of topology and differential geometry, and that replaced tensor calculus. And then the emphasis was on invariantly defined structures. The figures and the pictorial representations that in this monograph really were vital in the way that the subject subsequently developed and the way that we think about it. And it's really, to me, remarkable that all these developments were happening, and Stephen and George were PhD students at that time, right? I mean, just when these were happening, and then still in 1968 or 1967, when they actually signed this memorandum of understanding with the Cambridge University Press up here, it's kind of amazing, right? That first of all, they were in the mid-20s, barely in the mid-20s, and they had managed to absorb all this material, all this radical paradigm shift that was occurring, just as such young researchers, and then they really had the chutzpah, the courage, the foresight to think that they could actually write a monograph which actually put together in a comprehensive manner all this paradigm shift that was actually happening. I mean, to me, it is really amazing that they were able to do this actually, and also that it's not just a matter of confidence and courage, but they were actually able to write a very carefully drafted proposal, detailed proposal for the Cambridge University Press to accept this at that time. Of course, the monograph was published 5 years later. Part of it is because they were writing it, for some time, but also because of, as George just explained to us, the whole idea about publication there was on a different scale because of this proofreading and the making of the figures and so on. Okay, so the hallmarks of this this particular monograph are the following. That conceptual clarity, the mathematical rigor, and concise and precise statements that capture the essential underlying structures. As the authors explain, the Machian view is reversed in this monograph. Now, the Machian view, of course, has a very long history, but the most recent discussions at the time when Hawking and Ellis wrote the monograph were that due to Hoyle and Narlicker, and their discussions involved a new theory of gravitation. And a fundamental ingredient of this theory, motivated quite strongly by Machian ideas, was that vacuum solutions of Einstein's equations or solutions with a single particle source did not make sense, physical sense, because this is the Machian view that the whole local laws are determined by the whole global structure of space-time. And so in the present day terminology, this theory, for example, does not have analogs of the standard black hole solutions. Oops, I'm sorry. Yeah, it's okay. Sorry about this, but something went wrong here in my. Okay. Yeah. So rather than this Machian view, Hawking and Ellis considered local laws as being determined by large-scale structure of the universe. As being determined, instead of considering the local laws as being determined by the large-scale structure of the universe, Hawking and Ellis take the local laws to be experimentally determined and explore what these laws imply about the large-scale structure of the universe. And there was this question about what large-scale structure of the universe meant, and they meant astrophysical and cosmological phenomena, as George explained. This insightful switch guides the discussion throughout the monograph here. So first of all, as I mentioned, the Hoyle and Narliker ideas really came, I mean, they had motivated them to formulate the cosmological theory in the context of their theory of gravitation. And a key issue at that time was whether the universe had a finite beginning. And the Hoyle and Narliker steady state cosmology basically said that the answer was no. Now, prominent British cosmologists, including Herman Bondi and Tommy Gore, and in the beginning, Dennis Sciama, but at the time the monograph was being written, Dennis had moved away from it, really were strong supporters of this steady state universe. But the steady state universe is based not on general relativity, but on the theory of gravity that Hoyle and Narliker had proposed, that I mentioned before, in which there is continuous creation of matter. So in the steady state universe, by contrast to the steady state universe, the known cosmological and expanding solutions of Einstein's equations all had an initial singularity, but they are highly symmetric, and Kalatnikov-Lifshitz had a program aimed at showing that this was an artifact of high degree of symmetries. Their hope was that realistic solutions of Einstein's equations, which would not have any such symmetries, would be singularity free. Now, Hawking and Ellis themselves saying already in chapter 1 that it will be one of our main objectives to show that this is not the case, that the paradigm that was being pursued by Kalatnikov and Lifshitz school is not the case. And then seminal ideas of Penrose's, further developed by Hawking and others that George just explained us, that established that singularities are in fact generic. The techniques involved were radically new. This really is something that is important to emphasize to people, of the younger people, who sort of feel that, well, this was something that was obvious or was already known. This is not the case. For example, I had a conversation with Madame Choquet in the 1980s, and she told me that for quite some time, the French school did not really accept the results of the singularity theorem. The point was that for years, the French school had elevated the degree of rigor in general relativity research by hard analysis, by proving very carefully existence and uniqueness theorems. And this, I mean, there was analysis in these theorems, but it was not really a hard analysis of the type that they were used to. Rather, there were all these pictorial, arguments and geometrical pictures, and it may be plausible, it may not be plausible. The question was whether the differential equations of Einstein's tell us that singularities are generic or not. That was the point for them. And without this underlying hard analysis, the arguments to the French school, for example, looked too pictorial and loose to be fully trustable as rigorous mathematical results. Of course, by the time our conversation took place in the 1980s, the French school had completely changed their view, and they had begun to completely appreciate the value and the deep paradigm shift that these theorems had actually caused. So the techniques really were radically new, and the comprehensive treatment of singularity theorems in the monograph served to bring them to the mainstream, causing a decisive shift in the community away from the Kalashnikov-Lifshitz paradigm. And as monograph says, this was one of the main objectives of the monograph up here. Okay, now there is another part of the monograph which has to do with the global structure of exact solutions. In fact, it is about 63 pages long. It is the longest chapter. Although Hawking and Ellis say right away in the very beginning of the book that these solutions are not realistic because there are all kinds of high degree of symmetries and so on. However, they illustrate various possible behaviors. And indeed, much of our intuition about the global structure of space-time in physically realistic situations comes from the space-time diagrams in the chapter. Some of them had appeared before in the research articles, particularly by Roger Penrose and Brandon Carter, but they were not widely known. The unified and coherent presentation of the monograph had tremendous impact in terms of developing our collective intuition about what can and cannot occur and where the surprises lie. They enable us to visualize structures and the reason, and to visualize structure and make arguments, reason, using diagrams and geometry rather than long formulas and analysis. So let me give you a few examples about this. I mean, so as George mentioned, there's a large number of figures here, and they have been really, really instrumental. And my understanding is that really, by the time the figures were done and so on, it is really George who took the responsibility of overseeing this production of figures, as he explained, with the draftsmen in the geography department. So here is an example. So I just want to give you a couple of examples up here. Here is an example. This is an embedding of Minkowski space in Einstein cylinder. So what you see here, the cylinder is Einstein cylinder, and the shaded region is Minkowski space. And now what you can see is this is the clearest depiction of the global structure of space-time, which we don't see when you write in Minkowski metric in just coordinates and looking at it just in terms of tensor calculus. For example, here is a point at spatial infinity. It's a point. It's not a two-sphere. When you think about the spatial infinity, you think of it as a two-sphere. You go up to infinity along a time like on a constant time slice up here. It's a point. And then one can see that this point has a light cone. And that light cone, the future of it is chi plus, and the past of it is chi minus. So this kind of intuition that has been developed really came from this picture up here. So this is the clearest depiction of the fact that I0 is furthermore, I0 is fully characterized as a unique point in the Penrose completion, which is space-like related to all points in the physical space-time. There's only one point, and that is I0. That is a characterization. And this was really this has turned out to be very powerful in the subsequent developments. And that chi plus and chi minus are its light cone. And these properties, although they are written here in Minkowski space, as again, is a specific, very simple example, but they are generic features and that have shaped our intuition about asymptotically flat space-time. In fact, as you can see here, Minkowski space can be embedded in this Einstein cylinder. And several years later, it led Demetrius Christodoulou and Madame Choquet-Brougham to actually show that a very rigorous analytic theorem about global existence of solutions of Yang-Mills equations in Minkowski space, global, not local. And what did they do? They used two facts. First, that Yang-Mills equations are conformally invariant. And second, local existence was known. So they used the Yang-Mills equations in the Einstein cylinder with the local existence up here. However, Yang-Mills solutions, Yang-Mills is a non-abelian theory, just like gravitation, and so it creates its own charge. So if in fact Yang-Mills theory has a charge, then since the space-like surfaces here in this picture, in the embedding, because of I0, they have the topology of three sphere, that if you have a charge up here, then the Yang-Mills field would blow up at I0 up here. And they could not prove their theorem in that case. So they had to assume that the charge was actually zero, right? And these are things that are obvious to us from the pictorial representation, but they're far from being obvious if you just look at the partial differential equations and try to put existence and uniqueness. So the theorem is true for the Yang-Mills equations with zero charge. So this is an example of power of this diagrammatic techniques up here. The second example is really the de Sitter spacetime, and again, and its Poincaré patch, and its Poincaré patch. And what is sort of interesting here is that Poincaré patch is this part of space-time that is given to us. And these are kind of time-like lines in the Poincaré patch. So supposing I had in the Poincaré patch a time-changing dipole moment up here, or a time-changing electric dipole moment, or time-changing mass quadrupole moment up here, then it would radiate. But you can see that this radiation would never leave the Poincaré patch. It is all confined to this Poincaré patch. Now, these properties seem obvious by just looking at it. But again, they are far from being obvious just looking at the partial differential equations. Now, I want to go to the next topic, which is black holes. The final states of black holes are discussed in this monograph in detail, but even though the uniqueness theorems were actually lacking them. And that to me is again an example of this foresight and strong, good intuition that Hawking-Ellis had. So in this black hole case, they say that the gravitational singularities which occur are probably hidden behind the horizon. To the external observer, they appear to be a black hole. We discuss properties of such black holes and show that they probably settle down finally to one of the Kerr family of solutions. So this is what I meant by saying this, they could have said, well, we don't know what happens and so on and so forth. But no, they had a good intuition that it really is a Kerr family of solution. And assuming this to be the case, one can place certain upper bounds on energy that can be extracted. And then they go on to talk about these upper bounds up here. Now, these words were written at the time when many astronomers and physicists did not believe that our physical universe actually contains black holes. I mean, a lot of people had said, I mean, rather prominent physicists, yeah, there are mathematical solutions, but not every mathematical solution is realized in nature. And so there has been enormous work on gravitational collapse and black hole mergers in geometric analysis, mathematical physics, and numerical relativity over the 5 decades since these words were written in the monograph. The paradigm has continued to be valid. That paradigm that I described up here has continued to be valid. And moreover, the LIGO-Virgo discoveries have provided strong observational support for it. Now, the monograph described specific solutions because of this Kerr uniqueness belief. And the next solution is really the first solution, of course, the Schwarzschild solution up here. And we clearly see in this solution that there are 2 asymptotic regions. So this is the formula going from space-time to the Penrose completion of it, arriving at the global structure of Kruskal extension and its Penrose completion. These figures are reproduced in many subsequent books and continue to be the best depictions of the global geometry, even now 5 decades later. And so in this diagram, we see clearly that there are 2 asymptotic regions up here. We see that there are horizons and there is a bifurcate surface, that the Cauchy horizons, that the Cauchy surfaces up here actually pass through this bifurcate surface. All these global properties, which are not obvious by just looking at the picture, by looking at the form of the metric, sort of become very transparent in these diagrams up here. And similarly, there is the picture of the Kerr black hole up here. Here is a maximum extension and for the non-extremal black hole and for the extremal black holes up here. And again, we see the outer and the inner horizons. So if I start up here, we see the outer and the inner horizons up here forming. The inner horizons here, outer horizons. We see that if I start with the Cauchy surface, I got Cauchy horizon up here. All these properties become really clear and to us all today are obvious, but we should go back 50 years ago and we should sort of thank the authors for making it so transparent to us, which would never have been obvious just by looking at partial differential equations and looking at the analytic formula. And then final picture that I want to show is that of a black hole merger. And this is a famous figure. It's a pair of pants depicting the event horizon. So the event horizon is the outer tube up here. These are the two black holes. These are the what they call apparent horizons. The world tube apparent horizons are nowadays called dynamical horizons. So there are two dynamical horizons of progenitor black holes. They coalesce and then make a final black hole up here. The dynamical horizons, this picture actually made the cover of the Science magazine. Not this picture, but the picture based on it, which is the numerical simulation that was based on this picture by the Illinois group. And this is what really formed our intuition. For example, for several decades, I mean, many people, including me, really motivated by this picture, we thought that in fact, these dynamical horizons can just start up abruptly, in the middle of space-time. For example, up here, you got individual dynamical horizon, and suddenly a common dynamical horizon forms. Suddenly, poof, and in fact, I had this discussion with leading relativists, and it was they always said, "Well, but they can pop up, at any time or something." And this is an intuition that has been there for almost 45 years since the book was written, given by this intuition. This intuition turned out not to be correct, but this is such a fine point. But so I just wanted to give you one example of such a finer point, namely. In fact, the figure is remarkably accurate, but it's only in the just a few years ago, 2019 to 2021, that accurate numerical simulation showed that the progenitor, the dynamical horizon picture that are shown here is not quite right. They actually join on smoothly to the common dynamical horizon that I got up here, and therefore there is really continuously to this horizon. So in fact, this dynamical horizon don't pop up suddenly, abruptly in space-time. But I mean, this sort of serves to show two things. One is that really for decades, our intuition was driven by this. Like 99% of the time, it was completely right, but occasionally it was wrong. But it was also driven by these pictures that appeared in Hawking-Ellis so long time ago. So let me summarize, therefore. Like Eddington's book, this monograph is really is a quest for structure. In fact, there's a quote, namely, the subject of this book is the structure of space-time on length scales from the radius of the elementary particle to the radius of the universe. And the point is that the comprehensive treatment of singularity theorems and the analysis of black holes using global methods that emphasizes causal structure is a crowning achievement of this monograph. Now, Hawking-Ellis were quite well aware of the fact that we do not have a complete set of local laws, although they turn Machian view upside down and assume that empirically we know local laws, but they knew that we don't have a complete set of local laws, and therefore they used only certain general facts about what we know about local laws to restrict ourselves to Einstein's equations with matter satisfying suitable positive energy conditions. These conditions also allowed the Browns-Dickey theory, for example. But as George pointed out, at the time, people thought that they knew that scalar fields that are now used in inflation can violate these energy conditions. But they thought that these scalar fields really are associated with elementary particles, so therefore it will be really very localized and will not affect the large-scale structure. Now, the caveats of this book, George already mentioned several. From what we know now, 5 decades after the publication, there are some limitations. However, most of them refer to discoveries, as we just had a discussion at the end of George's talk, that were made much later. For example, although energy conditions seem natural in for classical matter, they are violated by inflationary potentials that are commonly used in cosmology. Similarly, there are no discussions of black hole thermodynamics, which was developed just as the monograph was being finalized here. And as George mentioned, there is a very nice discussion of these topics, these more contemporary topics, in Bob Wall's book, which came about a decade later. Now, there is actually one puzzling feature about this omission, and and that was about gravitational waves. I mean, George mentioned that gravitational waves, we knew about them since Einstein, but that was linearized gravitational waves. And there was a lot of debate between then and 1960s about the reality of these gravitational waves. But in the 60s, thanks to Bondi and Sachs and Roger Penrose and Newman and others, it was the theory in full general relativity and a coordinate invariant description of it, was known. And furthermore, this description, particularly due to Penrose, also emphasizes causal structures and global issues, particularly in null infinity. Perhaps I think it was really, at the time, the emphasis was, when the book was written or conceived, the emphasis, particularly in Cambridge, but also elsewhere, was much more on cosmology and the singularities in cosmology and the topics related to them, rather than on gravitational waves. And that might have been one of the reasons up here. But of course, George can say more about this. So let me just end with the retrospective. Well into the 1950s, research in general relativity was largely dominated by tensor calculus and partial differential equations in local coordinates. Thanks in large part to this monograph, new generations started thinking invariantly in geometrical terms, using spacetime diagrams and emphasizing causal structures that were first introduced by Penrose. The emphasis shifted to global issues, and as the title of the book says, and the shift that subsequently created new frontiers, not only in relativistic astrophysics and cosmology, but also in mathematics. In relativistic astrophysics and cosmology, for example, the conceptual paradigm introduced by this monograph led to new ways of thinking about physical processes. So it's not just conceptual mathematical thing, but physical processes, and to new physical questions then in turn stimulated new observations. In mathematics, these ideas led to the detailed studies of cosmic censorship, nonlinear stability of Minkowski space and de Sitter space, and instability of anti-de Sitter space. Nonlinear stability of black holes is currently a very active area of research in mathematics. And more generally, I think it is fair to say that the monograph stimulated the creation of the area of geometric analysis to explore the issue of global existence using geometric structures that emphasize causality. In this respect, it has done significantly better than the Eddington monograph. Now, I just want to close with a personal note up here. As I said, that the book came out when I was just finishing my PhD, and therefore, for my generation and subsequent generation, it really has had very deep influence in the way that we think about general relativity and gravity and strong gravity. So immediately after my PhD, I went to Oxford, joined Roger Penrose's group as a postdoc. And one of the first things I did when I went to Oxford was to buy this copy of this book. So this is a copy of the book that I bought 50 years ago. As you can see, it is a well-worn copy of it. And you can see that it was only £3.95 at that time. And it is really very well-worn. I consulted, read it, consulted it many, many times. And I still have it. And really, it is clearly is really by far the best investment in a book that I ever made, a book of any kind that I ever made. Thank you.
Okay, well, thank you very much for that great talk. So now we also have time for questions. Let's see who wants to start off.
Getting late, I guess.
Let's see. Is there a question?
David?
Yeah.
Not a question, but a comment.
Yes, please.
I was a graduate student starting in 1967, just after the contract was signed, and I became George's second graduate student. we were very aware that the head of the group, Dennis Sciama, was still at that time keen on Marx's principle. So your Abhay's comments about the movement away from Marx are quite interesting. John Stewart, George's first student, and I used to joke together that if we wanted to get chucked out, all we had to do was go in the tea room and say loudly we didn't believe in Marx's principle.
That's great. Okay, thank you. Other questions or comments?
Well, this in a way reinforces my understanding. I mean, I was not sure about this, but my guess was that this Hoyle and Larlicker, particularly Hoyle's steady-state cosmology, was such a strong influence at the time, and that going away from it was a radical movement. And I think this book really did show that if you believe in general relativity with energy conditions, then initial singularity is inevitable. So that was really decisive moving away from the steady-state universe.
Okay, thanks. Other questions or comments?
I have maybe a very trivial question, because Abhay emphasized the fact that there are all these beautiful illustrations in the book, and that was probably mostly George works. So I have a very simple, naive question that was, what was the procedure at the time? Since now when we have to write a book on relativity, in order to produce this kind of images, we just use a computer by ourselves. And what was the procedure back then?
George, you want to talk?
Sorry, I'm slightly deaf. I didn't. Sorry, Abhay, could you stop sharing your screen now?
Yeah, I can.
Yeah. So the question was, what was the procedure for producing the figures?
Oh, I thought I kind of explained that. I sketched them, checked them with Stephen, and I then took them to this guy in the geography department, and he would produce a draft. He did it in black ink on high quality paper, and then I'd go back to Stephen. But of course, this was long before any of the computer ways of generating figures. And so it was all hand drawn, but with, he had ways of doing smooth curves and so on, but it was done by hand by a cartographer. But by the way, Abhay, just your very wonderful summary. There's two brief comments. One is, your Eddington's book was a great book, but what is very interesting, if you go back to that book and read it, you will find that you assume certain things that were there that weren't there. For instance, the way that the Bianchi identities were the second contraction of the full Bianchi identities, it just wasn't understood at that time. There were various things like that. And the other thing, you talked about money coming into the area just after the war. And some people may not know that at one point Ray Sachs was a corporal in the US Air Force, and the US Air Force was funding work there. And I think the idea was that the US Air Force was hoping that the general relativity community would provide an anti-gravity device. And I think that is why the US Air Force was funding people to work on general relativity. That's just a comment from the past.
Right.
Okay.
Yeah, you can hear me. So the George Goldberg, in fact, was the one who was asked to be the scientific officer in the Air Force base. And he is the one who gathered many people and then also handed out this funding. Ray Sachs was a student also in Syracuse. George was a student in Syracuse. Both of them were students of Peter Bergman's. And then Ray had moved away to Europe, but then they managed to get this funding from US Air Force to researchers in Europe to give to support research. And as you said, about there was the issue about the possibly anti-gravity, but there's also issue about they had heard that general relativity can provide corrections, so perhaps missiles could land much more accurately. That was another reason the funding. I mean,
Oh, okay, so that's actually a little bit more realistic given what turned out to be GPS and the fact that we still have no anti-gravity unless you count dark energy. So let's see. I think that Emanuele Berti, our host for the time, has a question or comment. So go ahead, Emanuele.
Sure. I just want to hear George's answer to Abhay's comment about the absence of gravitational waves. What was the thinking? Why is it really that cosmology took precedence, or?
We were focusing on cosmology, and I think it just hadn't become apparent how important gravitational waves would be much later on. So you can say we should have included it because there were all of the work about the asymptotic structure by Sachs, Bondi, van den Berg, Metzner, and so on. I think maybe it was partly fatigue. We'd got enough in the book and we didn't feel we wanted to put more in it. But if you like, it was perhaps, it could be called an error of judgment that we didn't see how fantastic the gravitational wave stuff would be today. Yeah.
Okay, great. So let's see. We have a question from Yinji Ma again. Go ahead.
Okay, thank you. Yes. May I ask two quick ones? One is to Professor Ashtekar, and you have mentioned that Hoyle and Nalica proposed their steady-state theory based on the steady-state cosmology, based on the gravity theory that they proposed, not GR. And that is something I learned today. So in that sense, I mean, I never heard about that gravity theory which Hoyle and Nalica proposed. But in that sense, I mean, was that theory being tested elsewhere in the other observational test? So if so, then we have an interesting situation by then. The then interesting situation that the Big Bang cosmology based on GR. The GR is well established, but Big Bang maybe by then was not. On the other hand, steady-state cosmology seemed to be more popular, but the gravity theory, which I'm not sure, may not be well tested. Anyway, so if you can comment on that, I'm just curious.
That made it, that tailored the theory so that for the solar system physics, really one could not distinguish between GR, the predictions, one could not distinguish between GR and then new theory appeared. But on the cosmological scale, there was continuous creation of matter, and that made the universe appear steady. You know, in other words, they thought the universe was not, they knew universe was expanding, and yet if it was going to be steady, then somehow there should be a continuous creation of matter. And so that was built into them in the cosmological setting. But they are tried to tailor it. I really haven't followed it in great detail in the past. But certainly when they first proposed it, they tried to make it so that the known tests of general relativity within the solar system were not violated at that time. But maybe Malcolm has something to add because, and also George, because they were there at that time. I wasn't.
Well, I just want to add something about this. They had an action at a distance theory, which was very interesting. And Hoyle had the idea, Nalica did the calculations, and there was a famous meeting of the Royal Astronomical Society where Hoyle presented this. And Stephen, as a graduate student, stood up and said, this theory doesn't work because the gravitational potential diverges. The integrals don't converge. And Hoyle looked at him and said, how do you know? And Stephen said, I calculated it. And that was a very famous meeting that took place in the Royal Astronomical Society when Stephen was just a graduate student.
I see. Thank you. And the And the other question I have is, just a little bit retrospectively. I mean, you both of you have reviewed many of the really great development in the decades and so on. I just wonder for the last 10 years, apart from the wonderful experimental discovery like LIGO, Virgo, and black hole imaging and so on, what is the theoretical advances that make both of you think are most important?
You want to go first, George? I mean,
yeah, you go.
Okay, so I think the theoretical advance, there are two different issues here. One is within general relativity and beyond general relativity. And I think the theoretical advances have to do with really understanding more clearly the structure of black hole horizons, the dynamical regime. The event horizons are not that useful because they're really constructed at the end. So this matching between gravitational radiation theory and exact general relativity and the horizons in the exact general relativity is very interesting. The ongoing advances in cosmology are also very interesting because there are many. I mean, CMB has been the Planck missions. The last data that came out is shows that the predictions of the standard inflationary model, if you want, are really borne out. And there may be other models as well, but they are borne out. But there are anomalies, and there are very, very interesting ideas that people are putting forward about, how to alternate ways about what happens and explanations for these anomalies. And some of them actually come from quantum gravity, having to do with the fact that, in fact, the initial singularity is not really singularity the way that that we think of, namely, it is not really the end of space-time. In fact, there is a very nice, you may want to see, there's a very nice video, it's very short, I know, 15, 20 minutes long, in which 7 of us were interviewed, including actually at that time, Stephen, Roger Penrose, Alan Guth, and so on. We were interviewed and we were asked about our views about the beginning of the universe. And everybody said that the Big Bang refers to a hot phase of the universe. If you believe in inflation, then after inflation and not before inflation. So there is a hot phase of the universe, but it's not really the beginning of the universe. So there is a very interesting ideas that are being proposed, are being pursued currently in the cosmological setting as well. And then on the mathematical front, I think this nonlinear stability, first of all, this result about instability of de Sitter was quite interesting to me because, it was unexpected. Then at the time it was, proved it was unexpected. But this nonlinear stability of black hole solutions and violations of cosmic censorship, certain formulations of cosmic censorships, they have been very, very fascinating. They have been very important advances. So these are some of the real advances that I can think of.
So briefly from me, I think there are 2 areas I would particularly emphasize. The one is the huge new understanding of structural formation and cosmology, its relation to the microwave background, and how microwave background observations give you information about structural formation processes. That's a huge area. Of course, the problem is we don't know what the inflationary potential is. We've got about 110 inflationary models, which is a problem. But nevertheless, there's been enormous important work there. But the other area is numerical relativity. And that's made incredible progress. And the whole black hole observations wouldn't be possible without some of that work in numerical relativity. And that's been a huge area that's been very important.
Oh, thank you. Yeah.
Yeah, so I think we want to move on to the next question. So I think Malcolm McCallum has a question or comment. Malcolm?
Yeah, I just wanted to comment on the US Air Force support. There was a Syracuse preprint by Josh Goldberg which wrote up that history. I have a copy somewhere. And there was also one of the people they supported was Bondi and his group in London, which also played an important role at that time. And I can remember seeing a bundle of papers in the King's College Library of the things that the Air Force had funded. So I think it is all documented, but probably not in a readily accessible public place.
Okay, great. Abhay or George, do you want to comment on the comment?
No.
No, the Air Force actually, as Malcolm said, has really supported quite a bit of research on asymptotic structure of gravitational field and on gravitational waves and so on and so forth. And that was quite important, I think, for a whole number of years. I mean, I think up the order of not quite a decade, but almost a decade. So that was really important.
Okay, great. Any further questions or comments? Let's see. Francesca Vidotto, go ahead, unmute yourself and say.
Thank you. So the book is quite, in an exquisite manner, a book about mathematical physics. And this was somehow what relativity was at the time. It was a subject that was studied mainly in mathematical physics groups and departments. And nowadays, we see relativity or maybe gravity in general being a subject that pertains astronomer, physicists, computational people, and so on. So I was wondering, from your privileged point of view, for the young people that approach now the study of gravity, what would be your advice, since, as I said, the study of gravity grew into such a large subject in which you can approach it from different perspectives and developing also different skills?
Abhay?
Okay, so I think that, I mean, the mathematical relativity is really quite alive. It's just it has moved more and more to the mathematics departments, right? In the sense of one is really doing geometric analysis as opposed to the kind of mathematical physics that was done by Roger Penrose, or I mean, in which really geometry is strongly used, but there's also analysis also much more strongly used than before. But within the physics and astronomy departments, if I look at classical relativity, then I think one of the things that the new people have to really deeply understand is really statistics. I mean, if I look at CMB, if I look at gravitational waves and so on and so forth, how inferences are drawn is not something that is taught to us in our physics courses. And the important of Bayesian statistics, important of, what to calculate, if you like, to show some events are likely, are probable, are not probable, and so on and so forth, or to interpret the actual observational data. This interface between mathematics, numerical relativity, and observations, that is really where the interface is, where the action is in gravitational waves. And in cosmology, again, understanding this data and understanding it. One has to understand the data. It is hard work to try to understand data, but I think the new generation should make an effort to understand how actually the data is analyzed. They don't want to do that in data analysis, but they have to understand how it is analyzed in order to know what are the interesting mathematical questions or mathematical physics.
I want to second that. I think that both in gravitational radiation and in cosmology, the statistics are central in that. And one of the key things is selection effects. And selection effects, you have to work out not just what you are seeing, but what you are not seeing. And what you are not seeing is as important as what you are seeing. It's the issue of the dog in the night. Why didn't you hear the dog bark in the night? And that's a key issue in cosmology, and for that matter, in gravitational radiation.
Right, yes. It may be in a lot of areas of science. Okay, so there is a question or comment from Marco Bruni. So go ahead.
Mine is a mix of a comment and a question, both for Abhay, George, and perhaps Malcolm. And one result of the study of singularities is that those of Robertson-Walker are very special because they are matter dominated. Then the Christian and Sachs paper that you gave me to study as a student, George, talks about velocity dominated singularities, and basically close to the singularity matter is completely irrelevant. And then partly to Abby is the question I'm a bit confused because you talked about this Kalashnikov and Lifshitz paradigm, but by then around 73, I think that also from that type of studies it was clear that there is a singularity after all. Also, this was the mixed master studies by Misner. But anyway, my question is, what do you think of the fact that giving up the strong energy condition, one gains the fact that then you can have non-singular models where matter is never negligible?
I think that's a very important result. I've published work on it with Roy Martins and other people, and there do exist these models which are non-singular, variety of them. And one needs to test if they are possible. But also let me emphasize something else. The underlying all of the cosmology stuff is the basic theme that the Robertson-Walker model is a good background model. And one of the issues is, can one test the Copernican principle? To what extent is that an observational testable principle? And quite a lot of interesting work has been done on that. And the whole back reaction issue, it do inhomogeneities act back and affect the cosmological dynamics. And there's been quite a lot of controversy about that, and there's still some very interesting stuff going on in that area at the present time.
Okay, great. So I think at this point, maybe I want to turn it back over to Emanuele Berti to see if he has any last remarks to say on behalf of the Society.
Before
we should probably end.
Sorry, there's one hand up from Vladimir Manko.
Oh, okay.
Oh, yes. Okay. Thank you. Hello. First of all, I would like to say that you, George, look very great because you did not change since many years that you came to Mexico, and I had a pleasure to talk to you. But I'm a little bit late. Probably somebody asked you this question about your book, brilliant book, which influenced so many generations of relativists. But are you going to prepare a new edition to your book, and are you going to change something in your book? Are you planning to?
Are we going to do a new edition? No, absolutely not. Stephen, of course, is dead, and I'm working in quite different areas now. I've got very interested in other areas of science, so I'm not working very much in cosmology or relativity anymore.
Okay, thank you very much. Thank you very much.
Okay, then I will just do some concluding remarks. I would like to thank both George and Abhay for the great historical remarks, and I found it all very interesting and enlightening, especially for younger people, and I hope that we will keep doing things like this because it's important to keep memory of what motivated masterworks like the one that we're celebrating today. And I would like to see you all very soon because we're gonna be doing more of these and we will announce them soon together with David. Stay tuned and see you soon. Bye.
Bye.